This brings us to our third, or maybe our second, type of intermolecular force. And this is a pretty deep rabbit hole that gets more and more interesting for me. So London Dispersion Forces, which I will abbreviate LDF every single time because that is a lot to write. You'll also see them called dispersion forces. These are a type of intermolecular force that everything with electrons has because it's due to electron position. And I'm going to scoot this up because we don't need to see those other things anymore. Roll on the screen. So this is instantaneous dipoles. Due to electron position. All right. So over time, especially with the nonpolar species, you would expect the electrons to be uniformly distributed. But since electrons are always moving, there's this probability, in fact it's quite probable, that you're going to have an uneven distribution at any instantaneous point in time. So since electrons are moving, right, it's possible to have an unbalanced distribution or an uneven distribution at any point in time. All right. So even if you have something that we have labeled as nonpolar, the electrons are moving, and on average, they might be somewhere other than uniformly distributed. And so let's take a look at something like this. I'll start with a simple example of an atom, and we'll just say we've got some nucleus right there, and then pretend that there's some outer region of this atom, and within that electron cloud area, we've got an electron. I'm looking to grab this pencil here. So it's possible that at any point in time, like maybe your electron's right there, which for a single electron atom, I guess it'd be polar in that direction. We're more worried about species with multiple electrons. But what I want to say is, okay, well, at another point in time, that electron might be over there. Or that electron might be over there. Now, what happens when we start to have multiple electrons is maybe at some point in time I've got an electron there, and they're balancing each other out, in essence, in terms of charge around the nucleus. But it's also possible that we end up with an electron there and an electron there, which is going to start to stagger our negative charge in that direction. And you might end up with some extreme case where you have those electrons both on that side at some point in time, in which case certainly you'd have a net dipole in that direction. And again, that's not a super realistic example, it's a single atom, but the more electrons you have, and keep that in mind for later, and the farther apart you can get those species, the stronger your instantaneous dipole can be. As a minor side note, and I'll draw this in pencil, you can get an induced dipole this way as well. If this end is slightly negative and this end is slightly positive, and you have some other atom next to it, what will happen is this slight positive end will pull those electrons that way, and it causes a dipole, and this one literally we call that an induced dipole. If we look at a slightly more complicated but classic example of just say diatomic hydrogen, H2, I'm just going to again fake a nucleus here, but there's our nucleus for one of the hydrogens, and there's our nucleus for the other hydrogen, and then there are two electrons that are shared between those two. And over time, you would expect this to be nonpolar, which is the electrons to be located, again, if it's a Lewis structure, localized between these two things. So maybe I'll put my electrons right there for now. And we have maybe a dipole that way and a dipole that way that will then cancel out. In reality, though, those electrons are moving, and at some point in time, you might have a situation where both the electrons are over here, where you have a clear dipole in that direction. All right, so it's all about electron position, and when those electrons are not uniformly distributed due to electron motion, we can get an instantaneous dipole, an instantaneous uneven distribution of charge, which, if you don't have hydrogen bonding or ionic or even regular dipole-dipole forces, then that's going to be the biggest factor in determining those things like melting point and boiling point and vapor pressure. Unsurprisingly, I have a lot to say about London dispersion forces, and I'm going to need more space than I have right there, but I do want our same column heading. The first of which is, as we're looking at London dispersion forces, these are due to electron position, so any species with electrons will have London dispersion forces, and that's something pretty important. Any species. And since my intermolecular forces initial handout is buried right now, I just want to hop back to this and our predictions, right? Is it ionic? No. Does it have a net dipole? No. Then you have London dispersion forces. And even if you have hydrogen bonding or dipole-dipole forces, you still have those London dispersion forces. And technically, even if you have ionic, you have London dispersion forces, because you just have to have species containing electrons. And the question is, and this one comes up frequently, like, how strong are London dispersion forces? We had written previously, I give up, we had written previously that London dispersion forces may be greater than, less than, or equal to in strength of London dispersion forces. And so how do we establish, like, how strong a London dispersion force is? We look at something called polarizability, which sounds like a made-up word. So we can assess the strength of London dispersion forces by polarizability. And I think if you just look at the word as it sits, polarizability, the ability to be made polar, right? And I'll put that in quotes. And why would this matter? Well, if London dispersion forces are based on instantaneous dipoles, if something is better able to become polar, it's going to have stronger instantaneous dipoles. All right, so that's some fundamental information there. More polarizable is stronger London dispersion forces. All right. So what we want to do is look at the key aspects of polarizability, and there are two of them, one of which is the number of electrons. All right. So the first key factor, the number of electrons. In determining how polar something can get, how uneven a charge distribution can be, the more electrons you have, the more unbalanced that distribution can be. And you'll have bigger numbers of electrons on one side, bigger charge disparity from one side to the other. So in terms of key factors here, the number of electrons increases gives you something that is more polarizable. And what does that more polarizable mean? It means stronger London dispersion forces. So considering two equal species in terms of geometry and nonpolar, the one with more electrons is going to be more polarizable. And I guess I should clarify there, I wrote number of electrons. More polarizable is going to be more electrons. And I'm just going to declare this outright. It is a very common misconception that the mass of the atom or the size of the atom is the factor. No. Number of electrons is what matters, because those are the things contributing to the charge. It does turn out that bigger atoms tend to have more electrons, but that is not the reasoning. The reasoning is the number of electrons. So when you're asked on a test or whatever, don't say the bigger atom, or the more massive atom. You would say the atom with more electrons. So be very careful with that. It's a common mistake. And then the other key factor for polarizability is something I will describe as length. All right. And you'll see what I mean in an example, but the short of it is, the farther apart you can get that charge distribution, then the stronger the instantaneous dipole will be. It's a vector, and given the same number of electrons, if they are farther apart, you get a larger dipole. So in terms of length, and I'll be more careful here how I write this, longer, and I'll put that in quotes, is more polarizable. And what does more polarizable for our purposes mean? Fundamentally, stronger London dispersion forces. And knowing these things right here, I want us to take a look at two classic examples where the answer is London dispersion forces. Our first example is going to compare two isotopes of C5H12 pentane, one of which is N-pentane and one of which is neopentane, and you don't have to know anything about organic chemistry or anything else to do this type of problem. What you need to be able to do is look at the structure, look at the numbers, and then make a correlation between the structure and the numbers based on intermolecular forces. So you'll notice the N-pentane 36 degrees Celsius, neopentane 10 degrees Celsius for boiling points, and you'll also notice that I wrote them backwards the first time, and I had to go back and redo it. Let's then take a look. Both of these things are nonpolar. All right, so if we're looking at our hierarchy of intermolecular forces, they're not ionic. They don't have a net dipole, so our answer is London dispersion forces. All right, so they're both nonpolar. So if there is a difference, then that difference is going to have to be something related to London dispersion forces or polarizability. Okay, so we're looking at polarizability. There must be some difference in polarizability. Our two key factors for polarizability that we had mentioned were the number of electrons and the length, as we called it. And so a quick glance here says, oh, if they're both C5H12, they both have the same number of electrons. So the only possible answer we can have is something to do with length. And I think if you glance at the pictures, you'll see that this structure, this chain of carbons, is a certain length. And the longest length we see in any one direction here would be 3 carbons. And admittedly, this is not linear per se, and this is not certainly not square planar. But very clearly, this one is a longer structure. So what can happen to our charge imbalance? Well, we would expect on average maybe our electrons to be distributed uniformly, but at some point in time we might have that staggered considerably to one direction. And in this case, they could not go as far apart. So how would we explain this difference? We'd say that both structures are nonpolar. They both have the same number of electrons because they have the same structure, but the N-pentane is longer and it's going to have stronger London dispersion forces. N-pentane is longer, which is going to give us stronger London dispersion forces. And those stronger London dispersion forces, just so we finish out this thought, stronger London dispersion forces means more energy required to separate, which we can translate to as a higher boiling point. All right, and we've got one more example that I want to look at for London dispersion forces. This question takes a look at the phases of the group 17 diatomics. And so very often you're not given numbers, but you could be given the actual boiling points for these things. But the general trend is gas, gas, liquid, solid, which means that as we're going down, and this is an important thing to recognize, as we're going down, we're getting an increase in the strength of the intermolecular forces. So maybe we just want to write out that observation. We see, as you move down group 17, the boiling point, or the melting point, which would be fine in this case too, increases. All right, that's the first bit of information we need to observe. And then we need to tie that in to the idea that increasing boiling point means that the strength of the intermolecular forces is increasing. Therefore, the intermolecular force strength is increasing. And we need to figure out why. And what these all have in common is that they're all diatomics, right? They're all nonpolar. So what do they have in common? That's what we start with. They're all nonpolar diatomics. right? They have two of the same atom attached to each other. So nonpolar quickly jumps us down our flowchart here. Is it ionic? No. Does it have a net dipole? No. London Dispersion Forces is our only choice. And so if there's going to be London Dispersion Forces as an answer, there's going to have to be some difference in the 7-syllable word that is polarizability. So, so if they're all nonpolar, then the answer has to be polarizability. And we said there's two key characteristics for that polarizability, the first of which is the number of electrons. And then the second, we said, was length. And so as we look at these, overall, these are linear diatomics, and length is going to be pretty similar, or at least comparable. I mean, iodine is much larger than fluorine, but proportional to the number of electrons, I think we can say that the length is pretty consistent. So that's not going to be our factor, which means that number of electrons is our key factor. And if you go down this group here, you'll see that our number of electrons increases drastically. We have 18, 34, 70, and 106. So what happens here as we go down this group, there are more electrons, but the same length, and they're both nonpolar, so we end up with much stronger London dispersion forces. Harder to separate the particles, and a higher boiling point or melting point, all right? So in this particular case, we'd say that moving down group 17, we have more electrons, right? Therefore, stronger London dispersion forces, right? Which we said particles will be harder to separate, so we're going to see this trend of increasing boiling points and melting points. And there we go.